Okay, thanks, Kelly. Hey, everybody, I'm Pete Millett, Staff Technical Marketing Engineer at MPS. Today's webinar, we're going to talk about how to choose the right stepper motor driver. I've been working with motor driver ICs for about 20 years, doing product definition and systems and applications engineering at MPS and at TI. And before that, I worked for a lot of years as a board-level hardware engineer. Here's the agenda. First, we'll review the basic operation of stepper motors and stepper motor driver ICs. We'll look at features and parameters on typical stepper driver datasheets and see how they relate to the motor's operation. Finally, we'll show you how to interpret datasheet specs and translate them to the real world. You'll find that you have to do some work yourself and not believe everything you read on the datasheet. First, let's review the basic construction and operation of stepper motors. So there's two common types of stepper motors, the permanent magnet stepper motor and the hybrid stepper motor. Although their construction is different, both rely on a rotor with permanent magnets and coils on the stator, the fixed part of the motor, to attract and repel the poles of the magnet. Most stepper motors use two phases, although three-phase and five-phase motors also exist. For this webinar, I'm only going to discuss two-phase bipolar steppers. These motors have two windings, which are driven 90 degrees out of phase like sine and cosine waveforms. Permanent magnet steppers are usually made with a ceramic magnet rotor that's magnetized with several segments alternating north and south poles. The two coils are wound on iron cores that have teeth bent down to form alternating sides to concentrate the flux and give north and south poles. Two of these assemblies are stacked, so hence the name can-stack stepper motor. Hybrid motors use a two-section iron rotor with small teeth and a magnet inside that makes the teeth on one section all north poles and the teeth on the other all south poles. The two sections are offset, and then coils are wound on pole pieces that also have teeth. To drive a two-phase bipolar stepper motor, usually regulated currents are driven through the two windings. The current direction is alternated to cause the motor to move step by step. The two windings are driven by two H bridges, which allows for current to be driven in either direction. The H bridges are controlled using a PWM waveform whose duty cycle is controlled by current feedback to maintain a regulated current in the winding. Usually, an integrated stepper motor driver IC is used to drive the motor. These parts generally integrate not just the constant current drive stage, but also a state machine to control motor operation as well. Drivers may have additional diagnostic and control functions too. The mechanical step resolution of the motor is set by the motor geometry, specifically the number of teeth or poles on the rotor and stator. Motors with between 16 and 400 steps per mechanical revolution are common. 200 steps per revolution is probably the most popular configuration. The stepper motor driver windings can be driven in different ways, which results in different mechanical motion. In full step mode, there's only one level of current driven, and only the direction is alternated between positive and negative. There's only 4 states per mechanical 4-step sequence. Non-circular half-step, which is also called 1-2 phase mode, introduces a state where one coil is undriven. This provides 8 states with intermediate positions between the full steps. Half-step mode is done by providing 2 current levels and 8 states. Quarter step has 4 current levels and 16 states, and so on. By modulating the currents in the 2 windings, the motor rotation can be controlled to finer and finer increments. This is referred to as microstepping. The currents are driven with sine and cosine waveforms broken up into some number of segments. For example, 1/8 step microstepping divides each full mechanical step into 8 pieces. All right, now let's look at what's inside a typical stepper motor driver IC. So this shows what's inside a typical driver IC. This is the MP6500. The high current driven through each winding of the motor is controlled by an H bridge consisting of 4 N-channel MOSFETs. There are FETs on each side of the winding that can drive to either the input supply or to ground. The FETs are controlled by current regulation circuits that measure winding current and generate a PWM to maintain constant currents in the windings. There's circuitry to drive the FETs as well as internal power supplies to generate the needed voltages to run the part. There's also some control logic which implements the state machine to control stepping, called an indexer. More advanced stepper motor drivers may contain several additional features. The MP6602 shown here uses a SPI interface to access additional diagnostic and control functions. It can directly measure motor back EMF, which allows it to implement rotor stall detection. Very sophisticated stepper drivers may also include motion profile generators, which can be programmed to automatically ramp up the motor speed from 0, move some number of steps, and then slow back down to stationary with one command. The feature set you need in the driver depends on your application, as well as how much is implemented in a system microcontroller. So on a typical stepper motor driver datasheet, you'll usually see a list of basic features on the first page. These features are the first things you need to consider when selecting the stepper driver IC. But as we'll see later, some of these features are really only guidelines. You cannot assume that they will all apply in your application. So we'll look at the important items one by one. The first feature or specification you need to look at is the supply voltage. What voltage you require will depend on the available supply voltages in your system, as well as the motor that you're driving. Since normally constant current is driven into the windings, the supply voltage is normally much larger than the rated voltage of the stepper windings. Often a 12 or 24 volt supply is used to drive 1 or 2 amps of current into a motor winding that actually only has a rated DC voltage of only a couple of volts. Next item is the output current. Unfortunately, this spec on the datasheet may be nearly meaningless, as we'll see in detail later. In any case, this rating must be equal to, or more likely considerably higher than, the current that you actually want to drive into the motor windings. The MOSFET on resistance, or RDS on, is important to determine how much power, how much current the driver can really deliver in your system. It's used for power and thermal calculations. Again, more on this in a minute. So the logic interface may differ from one part to another. Some stepper driver ICs have a separate logic power input pin, and the logic levels are proportional to that supply. Others have fixed thresholds. You need to make sure the logic inputs are compatible with your system. For example, if your logic only drives 1.8 volts, you'll have issues with stepper drivers that were designed only for 3.3 volt levels. So although most drivers have sort of a similar list of features, you should understand what really you need in your application, because more features means higher cost. Older drivers used an external shunt resistor, one for each H bridge, to provide the current feedback needed to maintain constant current in the windings. Those resistors are large and expensive. Most newer drivers measure the current inside the IC, eliminating the need for external sense resistors. The supported step modes vary significantly between drivers, anywhere from just doing full step up to 1/1024 step microstepping. To a point, finer step modes result in smoother and quieter operation, but often mechanical considerations limit the usefulness of very fine microstepping. For more information about that topic, read the article, Why Microstepping Isn't as Good as You Think, at monolithicpower.com. For quality motion control, the winding current has to be well regulated. One feature to ensure that is the control of current decay, which is that time when the winding current is driven towards 0. High motor speed and the resulting high back EMF can cause distortion in the current waveform if it's not properly managed. Older drivers dealt with this by using a fixed mixed decay mode, while some newer drivers with internal current measurement implement more advanced automatic current decay modes that provide much tighter current control. Application note 1AN120 at monolithicpower.com explains that in some detail. Protection features are necessary in stepper motor driver ICs. Overcurrent, overtemperature, under and overvoltage protection can save the IC in the event of a short circuit or a power supply problem. Fault indication is useful to allow your system to recognize that there's a problem. And finally, the IC package size can be an important consideration. Small packages can be needed to allow small PCB sizes, but smaller packages have higher thermal resistance, which means that they're less effective at dissipating power generated inside the IC. This may limit the amount of current that the driver can provide. There's no consistent way of specifying the datasheet current rating of a stepper motor driver. You might see the terms peak, continuous, average, RMS, or full scale, or no description at all, just current. And the meaning of these terms is often different between different vendors. This is made a little more complicated when you also consider what step mode is used. Since the winding current steps changes step by step, except in full step mode, the winding current can be described in a few different ways. More specifically, the maximum winding current, that is the highest current that's driven at any point during a step sequence, shown by this red arrow on this waveform, can be called different things in different data sheets. It might be called maximum current, might be called peak current, or full scale current, or even just current. So whatever it's called, this is the current level that you need to consider when you select a driver. In full step mode, the maximum current is always driven in both phases. This is usually the worst case situation in terms of power dissipation in both the motor and the driver. In full step mode, the RMS current driven is equal to the maximum current. It's essentially DC, even though the polarity is flipping back and forth. For power calculations in step modes other than full step, you can multiply the maximum current by 0.707 to get the RMS current driven through the winding. However, even if the datasheet rating is high enough to accommodate the current you want to drive, there's no guarantee that a particular driver can meet that current requirement in your application. Most of the time, thermal limitations, which include the RDS on, the IC package thermal resistance, PCB construction, and ambient temperature, will limit you to a current that's lower than the rated current of the driver. So before we dive into determining what the real current capability of a driver is, we need to understand power dissipation in the driver IC. So there's 4 MOSFETs in each H-bridge, although you might think of the FETs as switches. They're normally either on or off. When they're turned on, they have some resistance. This on resistance is called RDS on. Each MOSFET in the 2 H-bridges may or may not have the same RDS on. During current regulation, most controllers will hold one leg of the H-bridge low and PWM the other leg. During PWM, the duty cycle varies. It depends on the supply voltage, current regulation set point, and motor speed, which drives the back EMF, which subtracts from the supply voltage. The duty cycle can theoretically vary between 0% with only the low side on and 100% with only the high side on. But in reality, most of the time, the duty cycle varies around 50%. Given this, there's a little advantage to making the low side MOSFETs a bit bigger with lower RDS on than the high side. So you'll see that in some data sheets. So as an approximation, the winding current will flow through one low side and maybe half of the time through the other low side and half of the time the other high side. So you can estimate then that the total path resistance for one H-bridge as a low side plus the average of the other low side and high side. So 2 parts shown here. This is a result, this shows the typical path resistance of 350 milliohms for the MP6500 and 900 milliohms for this competitor part. Note that those are at 25 degrees C, room temperature. Unfortunately, life's not quite as simple as it first appears. MOSFET resistance, the RDS on, is not a constant value. It varies a bit from one part to another, which is why you'll usually see both typical and maximum values in a datasheet. For a worst case analysis, you can use the maximum numbers, although that's a pretty pessimistic approach, since there's usually quite a lot of margin between the datasheet limits and real life. But a worse problem is that the RDS on of the MOSFETs varies with temperature. This variation is due to the physics of the device, and it's pretty similar for all IC processes. This graph shows roughly what happens to the RDS on as the temperature increases. The problem here is, as the temperature increases, the RDS on increases. That means the power dissipated in the FETs goes up, so the temperature goes up more, and the RDS on goes up even more, so you can see the problem. You can be very conservative and just calculate power dissipation using the expected RDS on at the temperature that would cause thermal shutdown, which is often around 150 degrees C. And if you're not careful with the PCB design, you might very well get to such extreme temperatures. So to figure out the total amount of power dissipated in the driver IC, we need to add up all the power dissipated in different parts of the IC. The biggest part of this power dissipation is almost always power that's dissipated in the H-bridge FETs. Since motor current's flowing through this resistance, it dissipates power equal to I squared R, where I is the RMS current flowing through the winding, and R is the RDS on of the two MOSFETs together. And remember, with an H-bridge, there's current flowing through two FETs, a high side on one side and a low side on the other. Current regulation of the winding is done by pulse width modulating the FETs. When you do this, the power dissipated in the RDS on is proportional to RMS current flow squared. There's also an additional amount of power that's dissipated during the time the FETs are being turned on and off. That's the switching loss. This power depends on how long the FETs are in transition between on and off, which is the rise and fall times. During this time, the FETs are operating in a linear region like a variable resistor. So the power can be approximated by 1/2 times the voltage times the current times the rise or fall time multiplied by the switching frequency. So often switching data isn't published in a stepper motor driver datasheet. Most stepper drivers have rise and fall times of maybe 10 to 100 nanoseconds. Drivers that include a slew rate control can be much longer, up to 1 or 2 microseconds. So if there's no specification, I usually just use 100 nanoseconds as an estimate. Remember that a stepper driver has 2 H-bridges, so once you could calculate all this, you need to multiply the H-bridge losses by 2. And finally, there's static losses. These come from the logic and other circuitry in the IC that are always running. The power is simply the supply voltage multiplied by the current that the IC draws by itself. It's usually called the operating supply current or the quiescent current. So the total amount of power dissipated is the sum of all these. So from the last slide, we know that the total power dissipation is the sum of the resistive losses, switching losses, static losses. So let's use an example to do some calculations. 2 amps of peak current in the MP6500. So depending on the step mode, 2 amp peak probably means the RMS current driven is 2 amps times 0.707 or 1.41 amps RMS. Remember, the current driven is sort of approximately sine and cosine waveforms. The exception is full step mode, where RMS equals the full drive current, since there's only one current driven. By the way, that's why often step motor drivers will regulate the current at 70% of the maximum current in full step mode. So we don't have the rise and fall times in the MP6500 datasheet, so we'll use an estimate of 100 nanoseconds for rise and fall times. So in this example, with 2 amps of peak current at 25 degrees C, we come up with a total power dissipated of about 1.58 watts. So once we know how much power we're dissipating, we need to understand what effect that'll have on the temperature of the IC. What we care about is the temperature inside the IC on the silicon, usually referred to as the junction temperature. Since we normally cannot measure the actual temperature inside the IC package, we rely on thermal simulations and calculations to determine how hot the silicon's getting. This is important because the silicon can only operate up to a certain limit, often 150 degrees C. Above that temperature, most motor driver ICs will shut down to protect themselves. The flow of heat from a hotter mass to a cooler one is a lot like the flow of current from a higher voltage to a lower voltage. The transfer is affected by resistance. In the case of thermals, that's a thermal resistance. Most IC datasheets will include a thermal resistance number, theta JA. This is the resistance in degrees C per watt of power of the heat transfer out from the silicon to the ambient air. Once you know the power dissipated in the silicon, you can approximate the temperature inside the IC by just multiplying the power times the thermal resistance, and then adding this to the outside or ambient temperature. Unfortunately, the thermal resistance number is heavily dependent on the PC board construction. The numbers you find in datasheets are all based on some standard construction. Usually a JEDEC standard called JESD 51 is used. JESD 51 has several types of standardized board construction. The one most commonly used in IC datasheets is JESD 51-7, which is shown here. JESD 51-7 describes a 4-layer board, 3 inches by 4.5 inches, 1/16 inch thick, with 1 ounce copper and solid power and ground planes inside. That's a fairly typical PCB construction, but it might be much different than the board that you need to use. Different layer counts, copper thicknesses, and board size can all have a dramatic effect on thermal resistance. If you're lucky enough to have access to thermal simulation tools, you can derive a pretty accurate thermal resistance. Otherwise, you have to estimate and make some educated guesses. There is a pretty big difference between a 2-layer board, where you only have copper on the outside, and a multi-layer board with solid planes inside. These two thermal images show the difference between a 2-layer board and a 4-layer board with solid inner planes. This was done with an MP6500 running 2 amps peak into a stepper motor. So you can see the 2-layer board, the case top temperature of the IC, which is what the thermal imaging camera really measures, is 84 degrees C. On the 4-layer board, the temperature is 56 degrees, almost 28 degrees cooler. All right, now that we know how to calculate the power dissipation and the junction temperature, we need to go back and look at those current ratings. So here we see a comparison of the MP6500 thermal resistance in 2 different packages, and this competitor part also in 2 similar packages. Note that the thermal resistance is roughly the same, 32 and 31 for the larger TSOP packages, and 36 and 40 for the smaller QFN packages. Note also that the maximum current rating of the MP6500 is about the same as the peak current rating of the competitor part. So one would be tempted to think that either part would be okay with a winding current of 2 amps peak, right? But wait, how can that be when the RDS on of the competitor part is almost 3 times that of the MP6500? So let's run those same power dissipation calculations on the competitor's part, again at the same conditions of 2 amps peak, 1.4 amps RMS. So for this competitor part with 2 amps peak current, 25 degrees C, we come up with a total power dissipation of about 3.83 watts. That's more than double the power we dissipated in the MP6500 with the same conditions. Also, I ran this estimate with the same rise-fall times as I did for the MP6500. This competitor part implements slew rate control, which is adjustable and can increase the rise and fall times to as much as 2 microseconds. That'll increase switching losses dramatically, which will raise the power dissipation. You need to consider that trade-off between power dissipation and slew rate, which can have a huge impact on EMI. So can this part really work at 2 amps peak in your application? Based on the calculations we just did, we can determine the temperature rise of each driver under those conditions. Based on that, and a maximum junction temperature of 150 degrees C, we can calculate the maximum ambient temperature that each part can operate at with 2 amps of peak current. The MP6500 gives us a temperature rise of 51 degrees, so it could operate at an ambient temperature of 99 degrees before the junction temperature reaches 150, where it would shut down. The competitor part can only operate at an ambient temperature of 32 degrees before the junction temperature hits 150. That means at room temperature, this part that on the datasheet is rated at 2.5 amps peak and 1.5 amps full scale, whatever that means, is very close to shutting down at room temperature, driving 2 amps peak. So most applications require an ambient temperature that's much higher than 25. Consider temperature inside an enclosure or in a car that's sitting in the sun. So you can work backwards to determine what the real maximum current is for a driver at a given ambient temperature. I won't go through the detailed calculations here. You have to solve a quadratic equation to work backwards, but it's just the same calculations we did earlier, only in reverse. So it's actually easier just to work through the equations like we did here, using different current levels until you find out what actually works. So you can see at room temperature, the MP6500 exceeds the current rating on the datasheet. The competitor part meets their full scale current rating, but is nowhere near the peak current rating. So I'm not really sure what this peak current rating even is. So from this, you could conclude that the datasheet current ratings are pretty accurate if you use the peak winding currents, and room temperature. That is, assuming you consider the full scale spec of the competitor part as the maximum current rating and just ignore this peak current rating. If one interpreted the peak current rating to be, well, the actual peak current, you would be disappointed. So at elevated temperature, 85 degrees C, both parts can deliver much less current, which you'd expect. In this case, 2.3 amps peak for the MP6500 and 1.4 amps peak for the other competitor part. So remember, we made all these calculations using typical room temperature RDS(on) and the JEDEC standard numbers for thermal resistance. You might not be so lucky, since the maximum current rating really should be calculated at a junction temperature of 150 degrees. The real RDS(on) will be significantly higher by like 50%. There's also a possibility that any given IC might not meet the typical RDS(on) specifications, could be higher, up to the maximum datasheet spec, although that rarely happens. All that plus your PCB design may not be as good as the JEDEC standard. Luckily, it might also be better than the JEDEC standard. So there's really two things you can do. One would be to perform all these calculations using worst case numbers, using the maximum RDS(on) at 150 degrees. It's likely that your result will be quite pessimistic. You may come up with half the current that we calculated above, but it would be completely safe. If you're designing a life or death product, it's a prudent thing to do. The other thing you can do, which I usually suggest, is to build it and test it. I've been surprised quite a few times by a circuit being able to deliver more current than the calculations showed. It's especially true if your PCB design has really good thermal performance with lots of heavy copper. So I don't think any IC vendors intentionally publish information on datasheets that's untrue, but since there's no standard ways of defining the specifications, the methods used and the definition of terms vary all over the map. Because of this, when you select a stepper motor driver, or really any power device, you need to understand the parameters and calculations that'll give you the actual performance characteristics that you need. Don't just take the top level datasheet ratings at face value. Okay, so that's it for the webinar on how to select the right stepper motor driver. So in summary, you can't rely on the high-level specs in a stepper motor datasheet. They may be defined differently from one to the other, or they may represent conditions that are far from reality. Sometimes they're downright misleading. So to determine the suitability of a given driver for your application, you have to do your own calculations using parameters like the on resistance of the output stage and thermal characteristics of the IC package. This, in combination with PCB construction, copper area, and ambient temperature requirements will determine if a given part will work for your application.
Great. Thanks, Pete. Lots of good information today. So if anyone has any questions at this point, we'll open it up for questions. If you simply mouse over the Q&A button at the bottom of your Zoom webinar interface, you can ask away. As we're waiting for questions, I'll also mention again that we are recording this session. It will be available on demand at monolithicpower.com/webinars, and we'll send you an email reminder by the end of the week here. All right, so our first question: what happens with power dissipation when the motor is stationary?
So generally speaking, it's pretty much the same situation as when the motor is moving. You can consider a couple of different conditions. If the motor stopped at the 0 degree position, think of a sine and cosine waveform. At 0 degrees, one winding will be sitting at 0 current, and the other will be sitting at its peak current. If you move 45 degrees off of that, then both windings will be sitting at 0.707 times their peak current. So if you average that out, it's pretty much the same thing. I mean, the dissipation might be a little higher or a little lower depending on where you are in the step table, but in generally it will never be higher than the current you calculated using just peak current times 0.707 times 2 windings.
Great, thank you. Looks like we got another one about all the math you were doing. Do you have a spreadsheet or some easier way of making the calculations you showed?
So I did create a spreadsheet. I'll see if we can't get that on the MPS website so people can use it.
Good, and we'll work with you on that one, Pete. Next one up. I guess they want a summary of your article, Why Microstepping is Not Good. Can you give a quick overview of that one?
I can a little bit. It's a fairly involved topic, actually, but the main thing to consider is the more you divide up a full step into microsteps, the less torque you have. It's called incremental torque. So if you're sort of think of the part being balanced halfway between 2 full step positions. In the full step position, the rotor and stator are lined up, so the flux is very high. As you move away from that point, the flux drops until it starts to go up again towards the next full step. So when you're microstepping and you're between the full step points, the amount of torque you can generate by making an incremental change in the current is actually quite small. So what happens? Let's say you just have a frictional torque load on the motor, and the load is such that in full step mode, the motor works just fine. As you go to a very fine microstep mode, what you find is that the motor doesn't move all the time. So you might give it, say you're in 1/8 step, you might give it 2 or 3 step commands, and then the motor will jump 3 steps. So in terms of positioning, it doesn't perform the way you would expect it to. Now, if there's no torque, it works pretty well. But it depends on the mechanical load on the motor. The other thing that messes you up is that motors aren't perfect. And, I've found cases where with a real stepper motor, you might actually get backwards motion. When you try to move forward a very small microstep, you might get no motion. You might even get backwards motion. So there are motors designed specifically for microstepping, which have much better mechanical control tolerances. But a cheap motor is probably not going to work really well above about 1/8 of a step or a 1/16 of a step.
Great, thanks, Pete. And I went ahead and threw a link to that article in the webinar chat. So again, if you guys Zoom interface, click on the chat, you should be able to see a link to that and go read the full article. All right, another one here. Does this information apply to unipolar stepper motors?
So yes and no. Unipolar motors are driven a bit differently. Instead of an H-bridge, normally there are 4 low side FETs. And there's a center tap winding that goes to the supply voltage. So the way they change the current direction is they either drive one or the other of these 2 low side FETs against the center tap to move the current direction back and forth. There's no high side. So what happens when that low side FET turns off is that the output pin will fly up because of the current through the inductance. And it usually gets clamped somewhere, often with an external diode or TVS, sometimes internally. So the power calculations are different, right? You still have to consider the current through the low side FETs, and generally they're only on half the time on each phase. And then you may or may not need to consider the power that's dissipated in the clamp, which might be outside the IC. Usually it's a little easier because most of the time unipolar steppers are just driven in full step mode. So these low side switches aren't pulse width modulated. They're just turned on and off. So that simplifies things a bit.
All right. It looks like the last of the questions. If anybody has one more, start typing quick and we'll hold on for just a second. All right. But it looks like I'm not seeing any more coming. So thanks, Pete, and thanks to all of you for attending. We look forward to having you at at future webinars as well. Thanks today.
All right. Thanks, everybody.